Hello students, welcome you all to the next session regarding discussion of a new chapter known as air standard cycles, which is a part of module number 1. So in the previous video lecture, we have discussed regarding introduction to applied thermodynamics subject. We have discussed the syllabus framed for the applied dynamics subject, as well as we have also discussed and revised some of the PVT relations, heat transfer and work transfer for various kind of thermodynamic processes. So in today's session, we'll be starting with a discussion of air standard cycles. And then already on the screen, you have seen the phone number has been displayed through which you can highlight, as well as if you have any doubts, you can send me a WhatsApp message, as well as you can send me an email to this email IDs, which you can see on the screen. So now we'll be discussing regarding today's session, that is air standard cycles. First of all, what is an air standard cycle? So if in an engine cylinder, if you are using air as a working fluid to check the efficiency of that particular engine, therefore we call this cycle as an air standard cycle. So normally the IC engines we are studying regarding the petrol cycle, diesel cycle, that is known as Otto cycle or diesel cycle. There the performance you are studying with the mixture of air and fuel together. But now for our analysis, if we consider only air as the working medium, then the analysis of those engines, we call them as air standard cycles. So before we study the analysis of the Otto cycle or diesel cycle and dual cycle, we need to make some of the assumptions. What are the assumptions? The first assumption, if you observe here, the working fluid which you're considering, it is an air. And this air, it is circulating in a closed thermodynamic system to form a closed loop cycle itself. Then during this circulation, whatever the compression expansion processes are coming, these are reversibly adiabatic in nature, or also we call them by a term known as they are isentropic processes. So therefore, the second assumption, it clearly states that all the compression and expansion processes are to be reversibly adiabatic in nature. Then the third assumption, it states that the specific heat of the gas at a constant volume as well as a constant pressure throughout the cycle, it has to remain same. Irrespective of the change in pressure and temperature, the Cp and Cv value for air, it has to remain same throughout the entire cycle. So you can see here, I have highlighted the Cp and Cv value for air. Cp for air, that is a specific heat at constant pressure, it is 1.005 kilojoules per kg Kelvin. Cv 0.78 kilojoules per kg Kelvin. Gas value for air 0.287, and specific ratio of specific gamma value is 1.4. Then similarly, students, once this analysis is being taken out, then the fourth assumption, it states that there should be no chemical reactions taken into account, which means the chemical reactions we are not considering, which means that should not go under any chemical changes. This is the fourth assumption. Fifth assumption, as we don't have fuel here, for this air standard cycles, the heat has to be developed during the combustion process. How it is developed? It is added from an outside source. Similarly, after the rejection time, the heat is taken away from the exhaust gas. It is done by the heat taken away from the working fluid, that is the air itself. These are the assumptions which we are carried out for the discussion of any air standard cycle. Then let us move towards the discussion of the first kind of cycle. We call it as the Otto cycle, or it is a constant volume heat addition cycle. So generally, students, if I draw a graph of this particular Otto cycle, that is a PV chart, how does it look? It looks something like this, students. This is a y-axis is the pressure, x-axis is the volume. So initially the process 1 to 2, students, it is compression of the air takes place. We call it as isentropic compression process, like this. Process 1 to 2. Then from 2 to 3, the heat addition next process takes place, and it takes place at constant volume. So therefore it is a vertical line. 2 to 3, it is an heat addition process. Then 3 to 4, isentropic expansion happens, like this. 3 to 4, isentropic expansion. Finally 4 to 1, heat rejection at a constant volume itself. So if I write this names of this curves, it should be like this. Here V is equal to C, constant volume heat addition. Here V is equal to C, constant volume heat rejection. Then these curves, they are isentropic compression and isentropic expansion, which means P into V to the power of gamma is equal to C. This is the PV diagram. And let us show regarding the heat addition happening here at the process 2 to 3, the heat addition happens. We name it as QA. Similarly, the heat is being rejected here. We term it as QR. And if this is with respect to the pressure volume diagram. Similarly, if we plot the temperature entropy diagram, students, it looks like this. That is temperature y-axis, entropy x-axis, and process 1 to 2, as we have discussed, it is an isentropic compression process, which means there is an increase in temperature. So you can see here, this is 1 to 2. Then heat addition at constant volume, that is increase in temperature here. It looks like this. That is two to 3. Again, 3 to 4, isentropic expansion process. Heat rejection from 4 to 1. This is the TS diagram. So as I said, this cycle was developed by a person known as Otto, hence we named it as an Otto cycle. And here the heat addition takes place at constant volume, so therefore it is also known as constant volume heat addition cycle. If you observe carefully, students, from the process 1 to 2, that is from here, from 1 to 2, the piston is compressing the air. So therefore, the air which is being compressed from position 1 to 2, we call it as compression ratio by the symbol RK, and the ratio of V1 by V2 is the thing which is the compression ratio itself. So therefore, on the representation, it looks something like this. You can see here, I have named all the curves. You should name all these curves. You should show the processes, which means you will get 1 to 2 marks for the graphs itself. Now, how to calculate the thermal efficiency of the Otto cycle? To calculate the thermal efficiency of Otto cycle, you need to write the heat transfer for all the processes, all the 4 processes. First process, process 1 to 2, isentropic compression, which you can see in the sketch clearly. So as it is an reversible adiabatic compression process, the heat transfer for this process, it is 0. Then process 2 to 3, constant volume heat addition. As heat addition takes place at this particular process, that is constant volume, it is Q2 to 3 CV T3 minus T2. Then students, for 3 to 4, it is a reversible adiabatic expansion process or isentropic expansion process. So therefore, again, no heat transfer, Q3 to 4 is 0. Similarly, for 4 to 1 students. Now the heat is being rejected and it takes place at constant volume process. So QR is equal to Q41 and it is CV T4 minus T1. So once you have written all the 4 processes, in that you have already seen here the heat addition takes place, here the heat rejection takes place. Then we need to write the thermal efficiency equation. So generally a thermal efficiency equation, we write it as thermal efficiency equation is equal to heat addition minus heat rejection whole divided by heat addition. So therefore, if I write this in this form, that is thermal efficiency of particles calculated as heat addition minus heat rejection by heat added, we have seen heat addition is MCV, that is at this particular point, students, you can see here, it is MCV T3 minus T2. Heat rejection is MCV T4 minus T1. So I will substitute those terms here. These terms are in common, they get cancelled, and on simplification, this term T3 minus T2 goes to the other side and it becomes in this form, that is 1 minus T4 minus T1 by T3 minus T2. And in the numerator part, if I take T1 as common and T2 as common in the denominator part, the equation reduced to this form, that is T4 by T1 minus 1 by T3 by T2 minus 1. Now what I want to do is, I want to replace these temperature ratios and the simplification has to be done. So for this, I need to take the help of the PVT relations, which I will be applying for the processes 1 to 2 and 3 to 4 only. So if you observe here carefully, students, for the isentropic or adiabatic process 1 to 2, I want to replace them with respect to the temperatures itself. So for the adiabatic or isentropic process, the PVT relation in the form of a temperature and volume ratio, we can write it as I said, students, for the process 1 to 2. Write it as T2 by T1 is equal to V1 by V2 raised to the power of gamma minus 1. So this you can see here. Similarly, what is V1 by V2? In the initial step, I have said from the piston as it is displaced from position 1 to position 2, it is nothing but the description of the air being compressed, naming it as compression ratio. So I have replaced this V1 by V2 as RK to the power of gamma minus 1. Similarly, if I apply this for the process 3 to 4, then I can write this as T3 by T4 is equal to V4 by V3 raised to gamma minus 1. Now, students, please observe here carefully. What is this process 2 to 3? It is a constant volume process, from which I can write it as V2 is equal to V3. Similarly, if you observe process 4 to 1, students, it is a constant volume process, which means I can write V4 is equal to V1. Now, if these simplifications I do in this equation, what I can write? V4 as V1 and V3 as V2, which means it takes T3 by T4 is nothing but it is V1 by V2 to the power of gamma minus 1, or it is nothing but it is RK to the power of gamma minus 1. A small manipulation. So therefore, it takes this form, and now if you observe 2 and 3, I can equate the temperature ratios to one another, that is T2 by T1 is equal to T3 by T4. Now what I will do is, I will interchange the terms. That is, I will move T4 to the upside and bring back T2 to the other side. So now it becomes like this, which means I can simplify, I can replace this term T4 by T1 is equal to T3 by T2 in the equation number 1. And you can see here it takes this form. So I just cancel these terms and I name this as equation for the thermal efficiency of a Otto cycle. So this video lecture is used to describe regarding the thermal efficiency of an Otto cycle. Okay, students, and I can write in this form of a compression ratio RK 1 minus 1 by RK raised to gamma minus 1. Thank you, students.